Welcome to the Walton Pi. Today we are going to be classifying relations. If you'll remember from a previous video, there are three main types of categories that a relation can fall into. The first of these is a reflexive relation. So a relation on A is reflexive if for every element A in the set A, the pair A comma A is in the relation. A relation on A is symmetric if whenever the pair A comma B is in the relation, then the pair B comma A is also in the relation. The third main one is a transitive relation. So a relation R on A is transitive if anytime we have both the pairs A comma B and B comma C, then the pair A comma C is also in the relation. If a relation is reflexive, symmetric, and transitive, then it is a very special relation which we call an equivalence relation. If R is only some of them, but not all of them, it is not an equivalence relation. An equivalence relation requires all three to hold. So let's start with a few examples and just practice trying to figure out if they are reflexive, symmetric, or transitive. So for this example, take a minute to try and see if you can figure out if it is reflexive, symmetric, or transitive. Hopefully that was enough time. If it wasn't, feel free to pause it and be able to unpause when you're ready. But this relation is not reflexive, it is not symmetric, but it is transitive. So the reason it's not reflexive is the pair B comma B is not in the relation R. For it to be reflexive, it would need to have A comma A, B comma B, C comma C, D comma D, and E comma E. It's missing several of them, but even if it was only missing the one, it would not be reflexive. It is not symmetric because it is missing the pair C comma A. Because we have the pair A comma C, we would need C comma A to be in there as well for it to even have a chance of being symmetric. There are other ones that are also not in there, such as D comma A or C comma B, but just because it is missing one of the pairs just because it is missing one pair, that is something that makes it not symmetric. Now, if you are to go through and check all the different possible pairs, it does turn out that this is transitive. There is nothing that breaks transitivity. So, now that we've done one example, let's do another one. Let's let R be the relation on the real numbers defined by the set of ordered pairs x comma y, where x is less than y. Take a moment to try and figure out if it's reflexive, symmetric, and transitive. Feel free to pause the video and unpause when you're ready to see the answers. Hopefully you were able to figure this out. Let's go through these one at a time. Let's see if we can figure out if R is reflexive. It turns out that R is not reflexive because the pair x comma x is not in R for any x. Because x is equal to y, x is equal to x, x cannot be less than x because we are dealing with strictly less than, not a less than or equal to. So R is not reflexive. It is also not symmetric because if x comma y is in the relation, then x is less than y, which means it is impossible for y to be less than x, which tells us that y comma x is not going to be in the relation. R is transitive though. If we start with two pairs, A comma B and B comma C, in our relation, we know that A is less than B and B is less than C. So we can put those two together to say that A is less than B, which is less than C, which tells us that A is less than C. So that tells us that the pair A comma C is in the relation. So yes, this is a transitive relation. Because it was not reflexive or symmetric, this is not an equivalence relation. Let's do another example. This time, let's let the relation be the set of ordered pairs x comma y, where y is less than or equal to x squared. Again, take a few moments to try and figure out if this is reflexive, symmetric, or transitive. Hopefully that was enough time for you to be able to figure out if R was reflexive, symmetric, or transitive. If we start with reflexive, we can be able to say that this is not going to be a reflexive relation, because the point 1/2, 1/2 is not in the relation. That is because 1/4, which is 1/2 squared, is actually smaller than 1/2, so we do not have y's less than or equal to x squared in this case. We can also say that r is not symmetric. We can find that the point 2, 1 is in R because 1 is less than or equal to 2 squared, but 1, 2 is not in the relation because 2 is not less than or equal to 1 squared. We can also say that this is not transitive. The points 2, 4 and 4, 16 are in the relation R because 4 is less than or equal to 2 squared and 16 is less than or equal to 4 squared. However, the point 2, 16 is not, because 16 is not less than or equal to 2 squared. Therefore, this relation is actually not reflexive, not symmetric, and not transitive. Our fourth example is going to be a very similar one to the previous one, except this time it's a relation on the integers rather than the real numbers. So, take a moment to try and figure out if R is going to be reflexive, symmetric, or transitive in this case. Hopefully that was enough time for you to be able to figure out if R was reflexive, symmetric, or transitive. Now, you might think that this is going to behave exactly like our last example, because the rule is still the same. And our counterexamples for symmetric and transitive actually still hold. So R is again not going to be symmetric because the point 2, 1 is in the relation, but 1, 2 is not. And it's also not going to be transitive because the points 2, 4 and 4, 16 are in the relation, but the point 2, 16 is not. However, this relation is actually going to be reflexive because for every single integer x, x is less than or equal to x squared. So that tells us that x, x is in the relation. The reason for that is if x is negative, x squared is going to be positive. So x is definitely going to be less than or equal to x squared. If x is 0, then we have 0 equals 0, so the condition is satisfied again. If x is equal to 1, we get 1 is equal to 1 squared, so it's satisfied. And if x is bigger than 1, x squared is strictly bigger than x, which means that yes, again, x, x is going to be in the relation. Our counterexample for the last one doesn't work here because our counterexample was the point 1/2, 1/2, which is not in the integers cross the integers. That point is not a valid point in this relation. So this relation is actually going to be reflexive. I hope this video was helpful and that you were able to understand relations a little bit better, as well as being able to figure out what kind of relations different relations are. If you would like to see some of my other videos, please check them out, and please like and subscribe. It helps me out quite a bit. Thanks and have a great day.